하는 게 오늘 첫 경험인데. 들어보죠.
늙은 나이에 첫 경험하시고.
그리고 한국어를 강연하는 걸 더 좋아하는데 오늘 제 동료를 위해서 영어로 하겠습니다. 그래서 제가 영어를 잘하는지 수학을 잘하는지 한번 비교 감상해 보시기 바랍니다. Okay. Let me start with the following problem. Okay, so among all domains of fixed volume in n+1 dimensional Euclidean space, which one has the least boundary area? So this is a well-known problem, and the answer is given by the isoperimetric inequality. It says that the ball has the least boundary area among all domains with the same volume as the ball. So I think this isoperimetric inequality is one of the most famous inequalities in mathematics. Professor 서동엽 doesn't seem to agree. Okay. So let me change this problem a little bit. Okay. So this is least boundary area, so the minimum, global minimum. And instead of the global minimum, let's consider the critical value. So which one has the critical boundary area? So critical, so it can be a local minimum, or it can even be local maximum. Okay. So then the answer is not necessarily the ball. Okay. And to consider this problem, we have to introduce the following definition. Okay. So we have to consider more general domains. Enclosed by the immersed surfaces. So it's an immersion. So, for example, we are going to consider a more general domain enclosed by this immersed surface X. Okay. So in this case, the enclosed volume is not only this whole domain, but we also have to add this part of volume. Okay. So for this more general immersed surfaces, the enclosed volume is defined as oriented volume, which is V of x equals 1 over n+1 integral over sigma x at nu ds. So nu is the outward unit normal. Okay? And x is the immersion, so we can think of it as a position vector in the Euclidean space. We can take this dot product. So we are considering not only the embedded surfaces but also immersed surfaces, and for these surfaces we consider this oriented volume with multiplicity. Okay. Then for this type of immersed surfaces, the critical surface has the following properties, and this property is obtained by the first variation formula, and I denote the absolute value for the area of the immersed surface sigma. So area of sigma is critical among all variations of sigma, preserving the oriented volume enclosed by sigma, if and only if sigma has constant mean curvature. By mean curvature, I mean the sum of mean curvature h equals sum of principal curvatures.
What is this bracket x and mu?
Dot product.
The vector in x.
Yeah, position vector.
Position vector.
Yeah. So this volume is x dot nu times ds over n plus 1. Volume of this cone. So integrate it along sigma, then you get the oriented volume, counting multiplicity. Okay, so the critical surface has to have constant mean curvature. Okay? So I'll use the notation CMC to denote constant mean curvature. Okay? For example, sphere, round sphere has constant mean curvature.
Sorry.
Yeah.
You are integrating over sigma. Sigma is the bound. X is and
Yeah,
sigma
so
is the boundary.
Yeah.
Okay.
Yeah.
Do you assume x is R3 or any other?
And in Rn plus 1. Yeah. So I have n here. Yeah. Okay. So sphere is the standard example for the constant mean curvature surface. Then how about the converse? What can you say about this converse? And Hopf made a famous conjecture about this converse. He conjectured that CMC immersion necessarily implies round sphere. This conjecture has been open for about 30 years, but in 1980s, Venti found a counterexample. So he constructed torus, immersed torus, which has constant mean curvature. Okay? So locally, it's like soap bubble. Yeah, yeah. This because of this variational property, soap bubbles are critical points. So square is the most common soap bubbles we can see. Okay.
It is a local minimum.
What?
But it is a local minimum.
Venti torus.
Yeah.
Yeah, sure. Yeah, it's a local minimum. Can't be a global minimum by the isoperimetry inequality. Yeah, it's not. Maybe it's a local maximum, I guess. Yeah, anyway, it's a critical point. Yeah. Okay, then. So, but still, people would like to make this conjecture, in a sense, true. So, we want to add extra condition to the CMC condition, so that the immersion becomes a round sphere. So what are these extra conditions which make the CMC immersions necessarily round sphere? And there are three such extra conditions so far obtained. And the first one is obtained by Alexandrov. He showed that every CMC embedded hypersurface is necessarily round sphere. So if you add this extra condition of embeddedness, then CMC surface has to be round sphere. Well, this is a well-known theorem in geometry and PDE. For example, if you here we apply the moving plane argument or reflection principle. So the idea is reflect this part of surface across this vertical plane to get this, and then move this vertical plane to the left together with the reflection until we obtain an interior touching point, and at this interior we can apply the maximum principle, because the CMC surfaces cannot touch each other from one side. Okay? So they have to coincide by the maximum principle.
I'm sorry, what is the exact statement of Alexandrov condition? Embedded of what?
Embedded CMC hypersurface with no boundary. Closed CMC embedded.
Not immersive. Not immersive.
Yeah, not immersion.
So
Yeah.
you're considering immersion that is embedded, then it's
Yeah. Because we have a counterexample for the immersed surface. Yeah. Okay. And Hoff himself gave an extra.
Alexandrov is the Russian person 100 years ago.
When did he die? Maybe some time ago, I think. He proved this in 1950s. 53 or 50. So it's very, yeah.
Alexandrov is the teacher of Kolmogorov, or?
Oh yeah.
I mean, the same person?
Maybe, yeah.
Russian. Maybe not. Kolmogorov is senior then.
No. Alexandrov and Kolmogorov, they are teacher and
Friends.
students, but they are lovers each other. They live together. I went their house. They
Oh.
live together.
Oh, really?
Yeah. So
In Russia?
in Russia, yeah.
Oh,
But in 1996 or so, it was 100th birthday of Alexander.
Oh, yeah?
So he's well over 100.
yeah, Hoff gave an extra condition. Immersed sphere. Similar to in R3. So if you assume that immersed surface is a sphere, then it has to be round. Okay? He used the positive Euler characteristic for this proof. Sphere is the only closed surface with positive Euler characteristic. And the third condition was obtained by Barbosa do Carmo. They assume that stable CMC surface is round. Yeah. And so far, we have thought about the surfaces without boundary. But from now on, let's consider surfaces with non-empty boundary. Okay, before that, I have to give a definition of stability. Okay, the second variation of the surface area of sigma is non-negative for all volume preserving perturbations. So the second derivative is positive. Local minimum.
So that means the ventral torus is not local minimum.
Right. Yeah.
So it's not local minimum, but extreme. What is that?
Maybe local maximum.
Local maximum.
Maximum?
Or maximum what sort of
Maximum would be small oscillation, increase the area, as surface area.
But you have to fix the enclosed volume.
Yeah, sure.
Yeah.
But you know, suppose that you have some one fixed the domain,
Yeah.
and you must manifold, then you oscillate slightly up down. You
Mhm.
know, then this volume is preserving, but
Yeah.
the area is increasing.
Yeah.
So there is no maximum, local maximum.
But maybe you can find one variation which decreases the area.
Only in one direction.
Yeah. By that I mean local maximum. So you have to consider index of the.
so it's like a saddle point or some direction.
Yeah.
So it's not local maximum, but
Yeah. Oh yeah. Right.
it should be
Yeah.
saddle or
Right.
index.
Yeah.
Maybe most index would be
Most
one.
index.
Yeah. Yeah. My terminology was wrong. Yeah. Okay, then let's consider a surface with non-empty boundary. One principal example is capillary surface in a wedge. It's a constant mean curvature surface with constant contact angle. like, okay, so wedge is the domain between two half planes, and is CMC surface, but the contact angle theta 1 and this angle theta 2. Theta 1, theta 2 are constant along this boundary and along this boundary. Okay. So this the half plane pi 1 and pi 2. And some results about the capillary surfaces in a wedge is obtained by, first result was obtained by McEwen. There exists no embedded annular capillary surface in a wedge W, wedge W, if the sum of contact angles is less than pi plus alpha. And there's another result obtained by a former student of mine, Park. He proved that embedded annular capillary surface in wedge is necessarily round. So consider a round sphere and cut this by this the wedge, then you obtain this part of sphere lying in this wedge W. Okay? So this is the only embedded annular capillary surface according to Bach's theorem. So there's no other annular embedded capillary surface which is not round. Okay, then let's ask a question to the capillary surfaces in a wedge, which are similar to these results, extra condition problems. Okay? So let's combine these results with these results in the wedge. So let's ask the following question. Is there embedded capillary surface?
When this manifold surface with boundary, then how do you consider the volume of the system bounds?
Oh yeah, so you have to use this part of boundary together with
as the boundary.
Yeah, part of the wedge becomes boundary. Yeah. So is there?
When you are considering the manifold with the minimum manifold surface with the boundary, then you always need some kind of these planes to cover this.
Yeah, So we have quite strong boundary condition that the boundary of the surface should always lie on
the plane.
On these half planes. Yeah. So is there embedded capillary surface of genus greater than 1? They obtained the results only for the annular capillary surfaces, so genus is 0. But is there higher genus surface? And partial result was obtained by McEwen. There's no such surface if the contact angle is less than 90 degrees. And is there immersed capillary surface in the wedge?
I forgot which side was the contact angle.
Yeah.
Which side? Inside or outside?
This side.
This
Yeah.
one?
Yeah. Yeah. This
So
inside.
this one is less than half. There's no such.
Right. Yeah. Yeah. So like this one.
Possible.
Yeah. So this contact angle surely is smaller than 90 degrees.
There is no such thing.
Yeah. Yeah. So, and what if capillary surface is stable? I'm mainly concerned about this problem. And I have a partial result as follows.
This one is the condition there.
Yeah, this condition.
What does that mean?
So local minimum.
This is
For any
so the
very
volume is which
fixed.
one is local minimum?
Interior volume is fixed, and the boundary area is local minimum.
Local minimum.
Yeah.
Stable in that sense.
Yeah. So I have a partial result, which is a joint work with Koiso, not husband Koiso, but wife Koiso.
She is in.
Norihiko Koiso is a
She's in Toku.
not husband is in Osaka, but wife used to be in Nara University, but she moved to Fukuoka, Kyushu University. Yeah. So we proved.
At least two Koiso. Husband and wife.
Husband and wife.
Yeah, yeah,
Both are geometers.
yeah, yeah.
You don't know.
지금가 또 이거 생각이 안 나서 그냥 고통이하고 손들이
Immersed capillary, hypersurface in a wedge, and stable, and contact angle is bigger than pi over 2, and this joint from the wedge, from the edge of the wedge, and boundary of sigma is embedded for n equal to 2, and or boundary of sigma is convex So it's embedded and convex for higher dimension. Then sigma is part of the round sphere. So we seem to have many hypotheses, but this condition, contact angle condition, for this stable capillary surface with contact angle smaller than 90 degrees experimentally tend to move toward this edge. Okay? So it eventually becomes part of the spherical cap. Okay? So it can't be stable. Okay? So in nature it doesn't exist experimentally. So this hypothesis is not so artificial. And as for this second hypothesis, disjoint from the wedge, there is a counterexample. And this surface is stable, but it's not round, and it touches the edge. This edge. So we have to have this hypothesis. So the only extra hypothesis we have had to impose was this embeddedness for the surface case and convexity for the hypersurface. Okay, then let's take a look at the capillary surface from a variational point of view. So what are capillary surfaces? So capillary surfaces are with constant contact angle theta I theta 1 pi 1 theta 2 pi 2 capillary surface is a critical point. Of the total energy for all variations. T with fixed enclosed volume. And this enclosed volume is the oriented volume 1 over n plus 1 times integral of x ds. But this is open. Sigma is open. So to make it closed, we have to consider this domain, d1 on the plane pi 1, which has the same boundary as this part of boundary of sigma, and this domain d2 on pi 2 with the same boundary as sigma on pi 2. Okay. And we can enclose sigma with d1 and d2. And by the embeddedness, boundary is embedded, so there's such a domain D1 and D2, but sigma can be immersed. Okay. What about this energy? This energy is the area of sigma plus some constant omega 1 times the area of D1 plus constant omega 2 times area of D2. In fact, constant omega 1 is exactly minus cosine theta 1, and omega 2 is minus cosine theta 2. Okay. So, yeah, so capillary surface is a critical point of this energy. So, here's the area of sigma, but we have to have extra values. And the contact angle appears on this constant omega 1 and omega 2.
One more question.
Yeah.
If you remove stable,
Yeah.
there are counterexamples. You told that the example there is the picture there is the counterexample for the case
It's joint from the X.
Yeah. Yeah.
And if you remove stable, maybe you know some counterexample or no?
Yeah, McEwen proved that if it is embedded and genus 0, then there's no counterexample. McEwen and Park. Okay? But if it is immersed, then we don't know. So far, no counterexample. Yeah. So that's why we assumed that it's immersed. Okay. So how do you prove this theorem? For the stable CMC surfaces without boundary, Barbosa and Okaruma used this variation. And they applied this variation to the second variation formula. And later, Venti gave a geometric interpretation of this variation. And he found that this variation comes from parallel surfaces followed by contractions. So this seems to be a strange variation function, but this has geometrically very simple. Okay, it's a combination of parallel movement and contraction. Okay, so with this geometric observation, Venti gave a very simple proof of Barbosa and Okaruma's result, that every embedded stable CMC surface is round. Okay?
Stupid question.
Yeah.
Capillary's hypersurface is a cylinder type, or what is the definition of capillary?
Capillary surface is CMC, constant mean curvature. So it's like locally it's like a soap bubble.
So it does not give any condition on this topology of this.
No condition, right?
So
That's why McEwen and Park assumed the annular. Yeah. So topology plays an important role in these theorems. Yeah, yeah. So you can easily have the counterexamples, I think. Yeah. Okay. So, okay, then what is parallel surface? Okay. Parallel surface is like this. Consider this domain. Then you move along the boundary in the normal direction by a constant distance. Okay? So this is sigma, and this is sigma t. So we move along in the normal direction by a distance of t. So this is a parallel surface. So that's a natural definition by using parallelness. Okay. Then we have one simplest example of parallel surface is parallel spheres. So this sphere has radius of r, and this distance is t. So this sphere, outside sphere, has radius of r plus t. Then this outside sphere has the area equals 4 pi times r squared. So r plus t squared. Okay. And this is what? 4 pi r squared plus 8 pi rt plus 4 pi t squared. Okay. And this, the first term is the area of the initial inside sphere. And this is, what is this? Actually, this comes from total first mean curvature. And this second coefficient comes from total Gaussian curvature. Okay? And so by this formula holds not only for these spheres, parallel spheres, but even for these parallel surfaces in a very natural way. So let me introduce the area formula for these parallel surfaces, which is a generalization of this variation, this area formula. Okay? So that's called tube formula. So here's sigma, and xt1 equals x plus t nu. So this is nu, and this is t nu. Okay, then the sigma. Okay, then area. The area of equals area of initial surface sigma plus t plus so this is a generalization of the sphere area formula, okay, for the parallel surfaces. And we also have the volume, interior volume formula, which is 4 pi over 3 r plus t cubed. Okay? And this is nothing but the integral of this with respect to r, with respect to t. So similarly, for the interior volume, we can just integrate the right-hand side to get the interior volume. So this is called the tube formula. And this first observation about this was made by a statistician named Hotelling, but that was generalized by Hermann Weil. So he obtained the first tube formula. So this is quite intuitive and very simple. But so even for this complicated hypersurface, we have this very simple volume formula, which reminds us of this sphere area formula. No error term, exactly. No error term. That's why this is so interesting. No error term.
So the second term, the first term can be considered as the integration of mean curvature.
Yeah, yeah.
The second term is
scalar curvature. In three-dimensional Euclidean space, this is the Gaussian curvature. But in higher dimension,
this corresponds to the last one.
yeah, this is Gauss-Kronecker curvature. Yeah, total Gauss-Kronecker curvature. Yeah.
Symmetrical.
Yeah, elementary. Yeah, yeah. So again, I'm using the elementary. So. And this holds not only for the surfaces with no boundary, but also in the wedge. So theta 2, theta 1. So let's move this tube formula. So this is sigma t, okay? And this is t nu, and d1, and d2, d1t, and d2t, and this is pi 1, this is pi 2. Okay, so this is one-dimensional version of the capillary hypersurface. So even for this surface with non-empty boundary, we have the same tube formula. Okay? And a nice thing about
You determine this angle of this.
this angle theta 1,
When this flat part
yeah,
expands.
this angle,
This D1 and D2
yeah,
moves to D1T to D2T.
yeah.
And then this the side the angles.
Yeah, they remain the same.
Huh?
They remain the same. For the capillary surface, this contact angle theta 1 is constant. So this is same as,
choose this one as the same angle.
yeah. So this is also theta 1 and theta 1.
So you're keeping T varies and still constant
Yeah,
angle and
all the time, for all t. Yeah, that's the point of the capillary surface. Okay, so we are going to use that, exactly that property to prove our theorem. So for this area, we have this tube formula. I have only 10 minutes, so okay, let me hurry up. So the first variation, unfortunately, by this variation, the boundary moves away from pi 1 and pi 2. So to move it back to pi 1 and pi 2, we use this translation, TA. So x2 equals p plus TA. Then x2t together composed with x1t. This boundary is moved back to pi 1 and pi 2. Okay. And okay, then let's take derivative of the enclosed volume when applied, when the two variations are applied to sigma. Okay. Then since the second variation is just a translation, it doesn't change the enclosed volume. So this derivative is same as this derivative of the first variation, first parallel surfaces. But we learned that, we heard that by the variational property of the capillary surface, derivative of this enclosed volume is equal to x1t minus cosine theta 1 d1t minus cosine theta 2 the area of d2t. Remember, note this. By this variation, volume increases by this much. So increasing rate of the volume is on this side of sigma. Increasing rate is the area of sigma. That's exactly this. Okay. On this side, increasing rate is the area of this. But this this thickness is not same as t. This thickness is minus t cosine theta 1. So smaller thickness. So that's why we have to have this extra factor of minus cosine theta 1. Okay. So we have the increasing rate of the interior volume. Then we have the tube formula for this, which is given here. And we also have the tube formula for these areas. Because these areas, d1t, when projected onto pi of tubes, parallel surfaces of d1. Okay? But if you project this onto pi, then you have this area, so interior area. So tube formula for this interior area has to be obtained by integrating this tube formula. So this is the original tube formula, but this tube formulas are integrals of the tube formula. So by adding up, we obtain the following tube formula, following result. The area of sigma minus cosine theta I di plus, this is constant term, and first order term is cosine theta I sine theta I, the length area of boundary of the I. This is first order term, and the second order term is and let's denote this as a polynomial. But by the variational property of the capillary surface, this is exactly equal to total energy of x2t composed with x1t of sigma. Okay. So by this variation, of the composition of x1 and x2, interior volume increases by this much. But the variations which are allowed to consider is the volume fixing variation. So we have to decrease this increased volume. And that can be done by the contraction maps. So here we introduce contraction. So the final variation is defined by the first two variations multiplied by a factor of st, which introduces contraction. Okay? So we contract this variation by this factor. Okay? Then we introduce this contraction factor in such a way that we contract this increased volume such that the resulting volume is the same as the initial volume. Then we want to have enclosed volume is same. Enclosed volume after time t is same as the initial volume, which is V0, initial volume. And let's introduce another polynomial for the enclosed volume, which is increased. So this volume has polynomial expression like this, t n plus 1. Then so when you contract by this factor, volume decreases by this factor raised to the power of n plus 1. In other words, s of t to the n plus 1 times v0 plus vn plus 1 t to the n plus 1. So after time t we have this volume, but we introduce contraction. So by contraction by this factor, volume decreases by s to the n plus 1. So this is resulting volume, which is required to be equal to the initial volume. And from this condition, we can obtain a condition for s to the n. So from this, we can solve for s to the n, which is an infinite series. So s to the n is complicated, but this is the point. Okay, so we have one condition for the enclosed volume. And now let's consider the surface area, surface energy. The surface energy of xt is equal to some factor times surface area of x2t and x1t. But when you contract by this factor, volume increases by this factor, but area increases by s to the n, not n plus 1. So you have only s to the n. And that's why we compute s to the n here. Okay? So combining these two, we obtain E0 plus E1 minus n over n minus 1, V1 over V0, E0 t plus E2 minus n over n plus 1, V1 over V0, E1 plus n to n plus 1 and plus 1 squared times 2 v1 over v0 squared e0 minus n and plus 1 v2 over v0 e0 t squared. Okay, then we assume that it's stable. So second variation of energy, initial second variation, has to be positive. Okay, so this second variation is exactly this coefficient of the t squared term. Okay, so this has to be bigger than or equal to 0, and then after some steps we can express this as follows. So this second variation equals times minus integral squared ds cosine theta I sine theta I Okay, so this has to be positive by stability. But by our assumption, contact angle is bigger than 90 degrees, so this is negative, so this factor is positive. And this squared term, so this term is negative. And you have minus sign here. And this is minus. But for this factor, we have the Minkowski inequality. Minkowski proved that this quantity is bigger, small, negative. Okay, so the total factor, the total second variation term becomes negative. So here we have positive, but here we have negative. So that means that this has to be constantly equal to 0. So that means each term has to be 0. So this has to be 0. That means it's umbilic everywhere. So that means the capillary surface is round everywhere, part of gray sphere. Okay, that's it. Stop here.